Hello and welcome to today's class. My name is Dr. Wanjala Titus. Today I'll be taking you through statistics and probability. And today we'll be looking at the normal distribution. Under this normal distribution, we are going to look at the moment generating function of a normal distribution. I will therefore say, in the previous class, we were able to look at the binomial distribution. We were able to look at the Poisson distribution. And today we are looking at the normal distribution. And we have been looking at the moment generating function of a random variable x. The moment generating function of a random variable x is always given by the expected value of the exponent tx. That's how to get the moment generating function of a normal distribution. But we all know that since normal distribution is a continuous distribution, whereby we will have a random variable x, and this variable will be continuous. And we always said the expected value of a continuous random variable is always gotten by using integration of the summation of the probability mass function. So therefore, since normal distribution is a continuous random variable, then we will be able to look at the integration from negative infinity to positive infinity. Then we will have the exponential tx. We will have the summation of or the probability mass function. But under the normal distribution, the probability mass function f of x, the probability mass function is always represented as 1 out of the sigma, the root of 2 pi. Then we will say exponential negative half, we have into x minus mu, which is the mean, over sigma squared. That is now what we call the probability mass function. Therefore, let us replace the probability mass function here with this one. Since it's continuous, we will say the integral from negative infinity to positive infinity, we will have exponential tx, then multiply by 1 over sigma 2 pi exponential negative half into x minus mu out of sigma but squared dx. Here it was also supposed to be dx. Are we getting that? As you can see, this one is our first constant. So let us move this one out as our constant first. So this is going to be 1 out of sigma, the root of 2 pi, the root of 2 pi, then the integral from negative infinity to positive infinity. Then already this one is eliminated. We remain with exponential t of x multiplied by exponential negative half into x minus mu all over sigma but squared dx. Are we getting it? Then we say, but z, a variable z, is given by x minus mu out of sigma. Then it means our x is going to be, it will be mu plus z it will be sigma z. Are we there? Sigma z. Then when we differentiate this one, dx over dx is equals to, this one will end, so we'll have sigma dz as dz. So let us replace those values with this variable x and dx. Then it's going to be the 1 out of sigma, the root of 2 pi, that's 2 pi, the integral from negative infinity to positive infinity. Then we have exponential t into x, but our x is this one. So our x will be mu plus sigma z. Are we there? Multiply by our exponential, our exponent, which is, this one is represented as z. Are we getting? So this one is going to be z negative z out of 2, but all squared. Are we there? But dx now is represented as sigma dz. Are we getting it clearly? Then what to do is, this sigma will cancel out with this one. I want you to elaborate the point, since this one is going to be multiplying both of these. So it's going to be 1 out of the root of 2 pi, the integral from negative infinity to positive infinity. It will be exponent t mu, are we getting, dot. This one plus means the laws of indices. It will be exponent t sigma z. Are we there? Dot. This one now is going to be exponent negative z out of 2 squared dz, as we can see. Yeah. So let us take this one out as our first constant. So this one is going to be exponent t mu out of the root of 2 pi. Then we integrate from negative infinity to positive infinity. Then now this one is cancelled out. We are remaining with this one only. Then it's going to be the exponent t. Let us now evaluate this one. It's going to be a half. We want to eliminate this negative. It's going to be a half into z squared minus this one now, which is 2t sigma z. Then we have dz. Are we getting it clearly? Then from there we will have the exponent, which is exponential, this was t mu out of the root of 2 pi. Then the integral from negative infinity to positive infinity. Then this one is going to be the exponent half into z squared minus 2t sigma z plus t squared sigma squared. Are we there? Sigma squared, z squared. But our interest is to look at this one out of 2. Are we getting? So it means we can still have here, we can still have exponential t mu out of the root of 2 pi, this integral from negative infinity to positive infinity. Then we have exponent half into z squared minus 2t mu z dot exponent t squared sigma squared out of 2. This is 2. Are we there? Yeah, good. We are good to go. So it means this one, let us take out this one as our constant now. Then it's going to be the exponent t mu dot exponent t squared sigma squared out of 2 all over the root of 2 pi, the integral from negative infinity to positive infinity. Then this one, when we express this one, when we expand this one, we will get the root of 2 pi. Are we getting it? So this one is going to be the exponential t mu dot exponent t squared sigma squared out of 2 out of the root of 2 pi multiplied by the root of 2 pi. Then this one and this one cancels out. Then we remain with the moment generating function of a continuous random variable x being equals to exponent t mu dot exponent t squared sigma squared out of 2. So in simple words, the moment generating function will be the exponent t mu plus this one half. Let it make it half t squared sigma squared. Then this one becomes our moment generating function of a normal distribution. This means that by the end of this lesson, at least we have understood something. If you haven't subscribed into my channel, remember to subscribe in order that in the next class, we will be using the moment generating function of a normal distribution to derive the mean and variance. Thank you for watching. Bye bye.